Today's Monday. Whoops. I got 300 subscribers.
To your YouTube channel?
Yeah. You know what? If I get like 500,000 more, they'll start advertising. Okay.
Advertisements on your channel.
Yeah, sure. Me too. Okay. You're pushing that what's free, aren't you? All right. Did I explain to you why you shouldn't give people with chronic bronchitis a lot of oxygen? Did I tell you what a refrigerator nurse is?
No.
Boy, you guys are really, yeah. Here. Are you kidding me? Hey, you relax. Everything's good. Sadaka? Oh, yeah. All right, hang on. We'll work on that. Okay, here we go. Ready? Okay, you guys ready back there? Okay, here we go. Now, I explained this to you. I'm going to explain it to you again. That every organ of the body has that nice thin layer that covers it directly, and then you have that thick layer that covers the inside of the body cavity. In the case of the lungs, you have that parietal pleura, that thick, tough layer that lines the inside of the thoracic cavity. And then you have the parietal pleura that covers the lungs directly. And I made mention, visceral. And I made mention of the fact that the visceral and parietal pleura of both lungs are separate, right? So, and this is very important. The pleural cavity, or the pleural space, there's negative pressure in there. So there's like a little vacuum. And this is the reason that you can't blow all of the air out of your lungs. And you wouldn't want to do that. It wouldn't make a lot of sense, right? So normally we breathe in 3 holes, 2 nostrils and a mouth, right? But if somebody doesn't like you and they stab you in the chest, right, that would be excessive. They would just say, I don't care for you, and then move on. But watch, if you come upon somebody like that who's got stabbed in the chest, the thing that you don't do is remove the knife. And the reason you don't is for 2 reasons. Number 1, you don't cut bread like this. You got me? The knife cuts both ways, in and out. So when you're pulling the knife out, you may cut a major vessel and kill the person. Say, yeah, that's bad. So you leave it in and you actually pack around that knife and then get them to the hospital. That's Spanish for hospital. I think that will be an extra credit question on the midterm. You pack it around so that no air leaks around the wound. Now, if somebody stabbed you, right, stabbed a person with a knife, then pulled it out and then ran, now you got a hole in your chest. You got me? So what they do is they actually put like a little one-way dressing on it. So let me see if I can do this. You know what? I'll show you. This is like a field dressing for this. So watch. Now try this. You can try this at home, or maybe even better, try it on your way as you're going home. And make sure that people see you doing it. So if you put your fingers on your ribs and you take a breath in, your fingers should get farther apart. You got me? So when you take a breath in, the distance between your ribs gets bigger. So if you have a hole in your chest, when you take a breath in, that hole will get bigger. So air gets sucked into the pleural cavity. But when you blow the breath out, the distance between the ribs decreases. So it shuts the hole down. So a tension pneumothorax is like a roach motel. Roaches get in, they can't get out. So air gets in, it can't get out. That's the tension. So with each breath you take, every breath you take, I'm watching you. So with every breath that you take in, you're going to be sucking air into the pleural cavity, but you can't get that air out. So it will begin to compress the lung. So what they do, a field dressing, is you actually take like a piece of cardboard or gauze, you'll put it over the wound, but you won't completely snug it tight. You'll tape it on 3 sides. So when they take a breath in, that negative pressure will slap it closed, but because it's not completely closed, when they blow the breath out, that air won't be able to, right, it won't be able to come in. You got me? And when they blow the breath out, it's no big deal because there ain't air going to get in. So that's what they do initially. Once they get them to the hospital, the emergency room, this is a life-threatening situation. Yep. You ain't going to fall down. What they'll do is a needle decompression initially. And this is an actual needle decompression. It's in Russian, so I'll translate for you. You don't need sound for this one because it's in Russian. It wouldn't help. So watch. There's the needle. This is the thoracic cavity. Now watch. The needle that they use is a big gauge. They put it between the ribs. And as you can see, there's a catheter around the needle. A plastic catheter, which will bend. Excuse me, metal don't bend. So you withdraw the needle, and there's a one-way valve on that plastic catheter where it will allow air out. It won't let air in. And what you'll see is the lung begin to reinflate. There's the lung. Now you pull the needle out because you don't want the needle puncturing the lung. And then the catheter is plastic, so it will bend as the lung begins to reinflate. Yeah, and there's blood vessels there too.
So after it inflates all the way,
yeah, then what they'll do is they'll put like a Vaseline gauze dressing on it. And then in some cases, what they have to do, if this doesn't work, they have to put a chest tube to suction in them.
that is impossible. Yeah, why don't they withdraw?
They want to make sure that it is completely reinflated. So if they pull that out and then they seal it off, there's still more air in that space. And a lot of times what will happen is it will get reabsorbed, but it'll take a long time to do that. A spontaneous pneumothorax is where you actually, the parietal pleural will actually rip away from the lining of the chest. A lot of people who have sarcoidosis, have you heard of that? That's a connective tissue disease where the parietal pleural will actually rip away from the lining of the thoracic cavity. And without any trauma. It's called a spontaneous pneumothorax. But those aren't as bad because the chest wall is still intact. So air is not going to get sucked in there, right? It's the tension pneumothorax that is bad for you. And let me explain to you why. So in clinical, they refer to it as a sucking chest wound. All chest wounds suck. This one actually does suck. So if you look at this x-ray, watch. The heart is supposed to be here in the mediastinum, but you can see this guy's lung is collapsed, his right lung is collapsed all the way to this point. And his heart is actually pushed over, and this is his left lung. So this is what's referred to as cardiac tamponade, where the left, the lung gets, there's so much air in it that it will actually begin to compress the heart, and you get what's called cardiac tamponade. And when the heart gets compressed, it can't fill. So you'll have shock, and it's a result of cardiac tamponade due to a really bad pneumothorax. And as you can see, when you learn how to read a chest x-ray, here's the chest tube. He's also got the little central line that goes into his heart. So this guy's really messed up. And your trachea should be in line with your spine. But his, you can see the endotracheal tube over here. So this guy is really, he's a hurting unit. And when you take an x-ray, x-rays get absorbed by dense tissue. The denser the tissue, the more x-rays it absorbs, right? So in a lung x-ray, you want a good lung x-ray, it should be mostly dark because air is in the lungs. Bones are really good for x-rays because bones are dense, so they're really good at picking up fractures. The other thing I'd like to point out is you got a big turd right here. He really needs to go. Right there. Anyway, these little pieces of metal, those are EKG electrodes, right? So they're metal, so they're going to be absorbed. So that's a tension pneumothorax. So the two treatments initially are needle decompression with a one-way valve, and then the ultimate treatment is chest tube dissection. And then they'll wait a couple of days, and then they'll take a chest x-ray to see if the lung is reinflated. But these are pretty bad. These are pretty bad. There's a lot of reasons. One is like the sarcoidosis. The other one is for pleurisy, an infection and inflammation of the pleural lining. That can cause inflammation. So that's not a tension pneumothorax. That's called a pleural effusion, where you will actually get fluid, like you know how you get like a blister and the fluid comes out when you pop the blister? Fluid builds up in that pleural space and compresses the lung. So when people get lung cancer due to like sometimes even with bleeding or inflammation, they have to go in, and because fluid is heavy, it settles at the base of the lung, so they do what's called thoracentesis, where they will withdraw that fluid. Tell me that makes sense. That's a tension pneumothorax. Yeah? Okay. All right. Here we go. A one-way needle decompression, right? So the air will not be allowed in, it will be allowed out. And you'll do that if you work in an ER, you will do that a lot. You'll do it a lot. And when you, here's the other thing, when people come in, there's a trauma, they're in a car accident, whatever. Because you don't know the extent of their injury, you can't be sedating these people. Do you understand? So if they have a pneumothorax, you have to insert that chest tube with them awake. And they're screaming. I told you about the two guys that shot each other? Yeah. And we were sticking a chest tube in a dude, and he's screaming, right? Because you can't sedate them because you don't know the level of their injury. Say yeah. So, yeah, and they shot him. Yeah. That's jacked up. I had a really nice set of scrubs, too. I got them. They gave them to you. But it was like all spurtulated with blood. It don't look good, you know. Okay. All right, here we go. Watch. You need to get this, right? You need to get this. I tried explaining it one way. It didn't work. I'm going to explain it the other way. Can you dissolve a gas in a liquid?
Yes.
Good. So Watch. One of the ways that you can transport oxygen in the blood is dissolved in the plasma of the blood. How is it measured? That's very good. It's called a partial pressure. And the reason it's called a partial pressure is because the pressure of the atmosphere is made up of more than just oxygen. You got me? Did I do the math for you? Okay, good. Clinically speaking, this is what you need to know. One of the ways to transport oxygen is dissolved in the plasma, and it's measured as a partial pressure, and it's abbreviated PO2. And because it's a pressure, it's measured in millimeters of mercury. And the normal PO2 is between 80 and 100 millimeters of mercury. You got me? Now, watch. Here we go. I'm going to try this really hard. The PO2 of the air that you breathe, the atmosphere, is 160 millimeters of mercury. That's the PO2. So what is the PO2 in the alveoli? Why is it 100? Okay, watch. Can you blow out all of the air in your lungs? So there inside your lungs is what's called a residual volume. The residual volume of your lungs is the amount of air left in your lungs after you blow out all that air maximally. There's a certain amount of air left in it. And that air has a PO2 of about 40 millimeters of mercury. Why? Because you blew it all out and you were still exchanging gas at the alveoli and the pulmonary capillary. So if you take air in that has a PO2 of 160 and it mixes with the residual volume air with a PO2 of 40, by the time that air mixes and gets down to the alveoli, the PO2 is what? It's 100. So watch. The reason the PO2 of the alveoli is lower than the PO2 of the air that you're breathing in from the atmosphere is because it's mixing with a residual volume with a relatively low PO2, because that air, that oxygen, is going into the blood. Do you follow that? Now watch. Because you got 40, right. You got air with a PO2 of 40. Then you're taking air into your lungs with a PO2 of 160. Right. When those two mix, you will have, by the time it gets down here, a PO2 of 100.
You're really just taking the average. That's why you're dividing it by 2.
Boom. I'm taking the average.
Got it. Okay.
I'm taking the average.
Got it. Okay.
You got me? All you need to know is this. The reason the PO2 of the alveoli is lower than the PO2 of the atmosphere is because that air that you're breathing in with the high PO2 is mixing with the residual volume. Say yes. Now, watch, just so you get this. If you could blow out all of the air in your lungs and then take a new breath each time, what would be the PO2 in the alveoli? 160. Because you are completely cleaning it out and then taking a new breath in. Say yes. Okay.
That's why we so hyperoxygenated.
What's that?
There is a Zen form of breathing where you breathe out as much of your air as possible, and then you hold the breath at the bottom to clear out any excess oxygen, and then you breathe in. That's why it hyperoxygenates.
Yeah, that's right. Yeah. And because we breathe by CO2, those real dudes that can stand under water a long time, they hyperventilate before they go under. So they breathe out more CO2 than they're producing. That way they can build up more CO2 before they're forced to breathe. Let's try it. We'll dunk some people's heads in some really cold water.
Awesome.
Just hyperventilate before we go in. Okay, here we go. Here we go. Ready? One of the ways that oxygen is transported in the blood is dissolved in the plasma. Say yes. I'm going to answer two questions in one. Ready? What kind of blood is pumped by the right side of the heart?
Deoxygenated blood.
So watch. This deoxygenated blood, essentially venous blood, is being pumped. Here we have an alveoli, right? And then you have a palm cap. P. Diddy. Say yeah. This venous blood that's being pumped, it has a PO2 of 40. What's the PO2 in the alveoli? Where do things always go? Watch. So that PO2, that air in the alveoli, will get dissolved in the plasma until the PO2 and the alveoli equilibrate. So the PO2 of this newly oxygenated blood is now 100. And the reason it remains 100 is because you are continually replenishing that air by breathing. Do you see this? So this newly oxygenated blood dissolved in the plasma with a PO2 of 100 leaves the pulmonary capillary, goes through the pulmonary veins, and is sent to what side of the heart? Please get that right. The left side of the heart. And what do you do in the left side of the heart? You go to the Faculty Staff Gateway homepage and hit log in. So you do. Then you hit Blackboard. Then you hit the number, then a password. I got a letter from the IRS. Watch. They said, you have a credit of $28,700, but we didn't get your taxes from 2015. So I forgot to sign my taxes, but they cashed the check. Can you believe that?
That's government.
Write this down. Write this down. 3 things you never want to get mixed up in. Federal government, legal system, or the mafia. They'll get what they want. Are you writing that down? You think I'm lying. What's the PO2 of arterial blood? Get this right, I give you extra credit. 100. You get 1 point of extra credit. So you should have asked how much. You ever look at this video of circulation?
Yep, I'll try. Like I look at it every morning.
Do you really?
Yep.
That's pretty disturbing.
It's my Zen mantra every morning.
Sweet. Sass. But here's the thing, and there's no getting around this. I have an Epic pen, and you don't. And that makes me better than you.
Your heart is a
Oh, yeah.
It's a
Here we go. Okay, watch. Where's the only place the gases and nutrients are exchanged? Yeah, something like that. Okay, so watch. What's the PO2 of this blood inside the left ventricle? What's the PO2 inside the left subclavian artery? What's the PO2 inside the brachial artery? That's very good. So if a doctor wants to find out what the PO2 of arterial blood is that's being pumped by the left ventricle, because the only place that nutrients and gases are exchanged is at the systemic capillary in the cell, they don't have to stick a needle in their heart. They can do it through an artery. Ain't that right? That's why they do arterial blood gases. We're going to learn about that. Oh, yeah. ABGs. I don't even know what that is. Okay, so watch. It's very exciting. Right heart, left heart. Are you watching that? And then you're down to the systemic capillary. Watch it. And then we have to draw the ever popular cell. If you get this right, big extra credit, big. What's a byproduct of metabolism? Oh, that's too late. CO2, right? What does the cell need to sit at the end of the electron transport chain in order to make it? That's good. What's the PO2 of arterial blood? Oh, gosh. Oh, wait. I can't do this. Yeah. Better write this down. The PO2 inside a cell at basal metabolic rate is 40. Where do things always go? So by pressure, oxygen is pushed into the cell until the plasma equilibrates with the cell. So the PO2 of venous blood is going to be after it's done. No, it's venous blood now. Your your hope is that cell is always using oxygen. Otherwise, if it was your leg would rot off. So if it's always using oxygen and maintains a pressure of 40, it is going to move from the arterial end into the cell until they equilibrate, where the PO2 inside the cell is going to be equal to the PO2 of venous blood, which is 40. Tell me you got that. And where do all the veins of the body dump their venous blood? Into the right side of the heart. And what's that PO2 of that venous blood? 40. Is 40. Look, it comes, bam! I got that spot too. It's a good day. I have the best day right there in my life. I hit that thing and it went right to the spot that I wanted it to go. What's the PO2 of venous blood? 40. Where does all the veins of the body dump their venous blood? Where the right side? Yep. And in the pulmonary capillary and the alveoli, what's the PO2 of the alveoli? 100. What's the PO2 of venous blood? 40. Do you see that? Mm-hmm. Watch. Why is it important that you can transport oxygen in more than one way? This is why it's important. When people are bleeding their own blood, can you look at that blood and say, that's A negative all day? Order me up some A negative blood. Can you? But you just learned today at Gateway Technical College, there is another way to transport oxygen other than bound to a red blood cell. And it is what? Dissolved in plasma. And what is plasma mostly made out of? Don't say what. Oh, this is advanced. 0.9% sodium chloride. So you start big-ass IVs on these people, you pound the fluid, you give them 100% oxygen, you get their blood, you send it to the lab so it can be typed and cross-matched, but you can keep this person alive because you can transport oxygen dissolved in plasma. That's top flight information there, Anna. So your job, your priority as a nurse, when somebody comes in and they're bleeding their own blood, is to stop their bleeding their own blood. Once you stop their bleeding, you start big IVs, and you just don't run it in at a drip. They actually have bags, pressure bags, where you will put pressure on that bag to push that fluid in. And what you will have to learn is how to start big old IVs on people who don't have big old veins, where you're talking about a 16 or 14 gauge needle. Those things are huge, right? And you have to practice that to get good at that. And you will have to do that, or that person will end up kicking it. What could you do if you couldn't get the IVs in, at least temporarily? What else could you do? They're bleeding their own blood. Well, okay, right? Well, where could you give them some extra blood? See, that's so good. See? Now, watch. Once you start working and you start working like an ER and ICU, that stuff will come automatically to you. Right? But you have to understand why you do it. When you understand why you're doing it, you do it quicker. You don't have to be told. Say yeah. Okay, watch. So what's one way that oxygen is transported in the blood? And how is it measured? It's measured as a PO2. What's the best way to transport oxygen? Yep. It is bound to a red blood cell on hemoglobin. All right? Not yet. Not yet. So the other way is bound to the iron on hemoglobin. So you have a red blood cell. Just so you know, and I explained this before, a red blood cell is so big that it does the la cucaracha right through the pulmonary capillary. It goes one at a time, right? That's how big these red blood cells, and that's how small a capillary is. So, and you have the big freaking protein, hemoglobin. Right? Here's hemoglobin. What's embedded in the heme portion of the hemoglobin? Iron. And there's 4 of them, right? And you better write this down. How many oxygens can bind to each iron? That's good. Okay, here we go. How many hemoglobin molecules does each red blood cell have? Ooh, that's so close. 250 million molecules of hemoglobin. So a red blood cell has so much hemoglobin, it ain't got no room for no nucleus, and it ain't got no room for no mitochondria. So what's the only fuel that a red blood cell can use if it ain't got no mitochondria? Fat enters the metabolic pathway as acetyl. Right. The only fuel that a red blood cell can use is glucose.
So that's to break it down to pyruvate
and 2,3-diphosphoglycerate. I don't want to talk about that. Ain't that great? Okay, so watch. You ready? Venous blood has about 70% of its iron have oxygen bound to it. You got me? Venous blood has 70% of the irons have an oxygen bound to it. So is there still oxygen in venous blood? We've established that, right? That's why CPR works. But what do you want to do when that red blood cell gets to the lungs? You want to, right, you want it to get like close to 100%. So watch. What's the PO2 of venous blood? What's the PO2 of the alveoli? Better write this down, better not pout. As PO2 increases in the plasma, it will cause oxygen to bind to the iron on hemoglobin. Tell me you got that. Now think for a minute. And this is where if you think, it will be good for you. Where do you want the oxygen to bind to the iron on hemoglobin? What part of your body? You're not thinking. In the lungs. Where do you want it to let go? At the cell. So watch. Better write this down. High levels of PO2. High PO2 cause oxygen to bind to the iron on hemoglobin. In your book, that dirty book, it's black. Did you see it? You know why? People rub it in the dirt. It says that high PO2 causes oxygen's affinity for hemoglobin to increase. That's a fancy way of saying that high PO2 causes oxygen to bind to the iron on hemoglobin. Say yes. Who's with me? Now watch. Watch. When you put the little red thingy, the little clothespin on somebody, what's that measuring? What? What's it measuring? Of what? What are you measuring? That's right. When you do the little pulse ox, you're measuring the amount of oxygen bound to the iron on hemoglobin. You got me? And normal arterial blood, 96 to 98% of all of the iron in all of the hemoglobin, in all of the red blood cells, should have an oxygen bound to it. Say yeah. Why isn't it 100%? I'm not going to tell you. Watch. That's for extra credit. Big extra credit. I'm not even going to put the question on there too, Anna. I'm going to forget. But if you write the answer down, you explain it good. Big extra credit. Big. Like 100 points of extra credit. Oh, yeah, here we go. Now everybody writing that down.
Why in the hospital does it usually come up like that?
There's always a little bit of error there.
Okay,
always. Yeah, because they'll get 100%, right?
Yeah.
You can never get 100%, and there's a reason why. I'm not going to tell you. It's extra credit. What? Right. If you draw arterial blood gases, you will never see 100% saturation of red blood cells. There's always a little bit of error. Just like an AccuCheck, right? There's like 2 or 3% error. Okay. What's the condition at the lungs? with respect to PO2? Is it high or low in the lungs? The PO2 is high, right? Right. It's going into the plasma. It's increasing in the plasma. And when the PO2 goes up in the plasma, it makes oxygen want to bind to the iron on hemoglobin. Where do all the red blood cells go after that? Huh? They go back to the left heart. The left heart pumps that blood down to the cells of the body. What's the PO2 of arterial blood? What's the PO2, or what's the PO2 inside the cell?
40.
What's the oxygen saturation of a red blood cell? Oxygen saturation of a red blood cell.
98.
There you go. So watch. Oh, it said oxygen.
Okay, so oxygen saturation.
Yeah, wait. Hang on, I missed that part. That's the best part.
Oxygen binding to.
Hang on, I got to get this. Now watch. Okay. So look. You got the red blood cell here. It's so big it's coming out of the capillary. You got hemoglobin. Looks just like that. Stayed up late last night doing that. Looks the same color. What's embedded in the hemoglobin? Same color. Right. But we're going to say it's just one because I don't want to draw too many. What's the PO2 of arterial blood? It's 100. Right? Can you see that? Yeah. What's the PO2 inside the cell? 40. You got me? So watch. PO2 is going to leave the arterial end of the capillary by pressure. So what's going to happen to the PO2 of the plasma of the blood? It's going to drop. And as the PO2 begins to drop, oxygen loses its ability to bind to the iron on hemoglobin. It will fall off and go into the cell. Oxygen dissociates from the iron on hemoglobin. How many people followed that? And under normal conditions, right, about 30% of the oxygen that is bound to the iron on hemoglobin moves into the cell. It dissociates. So what is the oxygen saturation of venous blood? 70%. About 70%. You following this? Okay. Watch. What's the byproducts of metabolism? I'm going to write these down. It's CO2, heat, hydrogen ions, ADP, and hypoxia, right? Low oxygen. What are these guys? Right, what do they do? No, thank you. They're massive arterial vasodilators. Who's with me? Okay, now watch. I'm going to show you something. What if this cell, let's say this is your hand, right, and your arm, and it becomes more metabolically active because you're reading the book and turning the pages like a madman. What's going to happen to the PO2 inside that cell because it's more metabolically active? That's very good. So now instead of the PO2 being 40, I'm making this up. The PO2 inside the cell is 100. I'm sorry. Look. The PO2 inside the cell is 20. Darn it. You got me? The PO2 inside the cell is 20. The PO2 of arterial blood is still 100. You got me? But now the pressure difference is greater. So more oxygen is going to leave the plasma and go into the cell by pressure because there's a greater pressure difference. So what's going to happen to the PO2 of the plasma in the arterial end of the capillary? It will drop, right? It will drop because inside the cell it's using more oxygen. And because it's using more oxygen, the PO2 of the venous blood at the level of this cell is going to be what? 20. And because the PO2 has dropped even lower than normal, it will cause more oxygen to fall off the iron on hemoglobin. Do you see this? So it is metabolism that dictates how much oxygen is delivered to a particular cell and what transports the oxygen down to the cells of the body. Right, and that's very good. I was just looking for a simpler one. Blood. Now watch. If a cell becomes more metabolically active, does it require more oxygen? And if it does, it will produce more byproducts of metabolism. Ain't that right? And the more byproducts of metabolism it produces, the bigger the arteries become. So when the little left ventricle contracts, more of that oxygenated blood is going to go to the parts of the body that need it. Do you have any idea how beautiful that is? It's perfect. How many people see this? It is metabolism that dictates oxygen delivery to the cells. We have now covered oxygen. What are the two ways that oxygen is transported in the blood? And we know now clinically why it's important that there's more than just the red blood cells, right? There you go. Okay, here we go. You got a cell. What's a byproduct of metabolism? Okay, I'll give you that. We're going to go with CO2. Can you dissolve carbon dioxide in the plasma? Good. So now if you get this right, I'm going to be real proud of you. I will be, because you're actually thinking. The PO2 inside the cell of a normally, basally metabolically active cell is 45 millimeters of mercury. All right? This is the arterial end of the capillary. What is the PCO2 inside the arterial end of the capillary? Before you answer it, I just want to know, is it going to be higher than 45 or lower? Lower. That's very good. That's exactly how you were supposed to answer that. Because where do you want the carbon dioxide to go by pressure? Out of the cell and into the plasma. That's beautiful. So the PCO2 of arterial blood is going to be 40. Now, the difference between PCO2 and O2 in terms of a pressure gradient is the CO2 is much smaller. But CO2 is like 20 times more diffusible. That's why you only need a small pressure gradient. So the PCO2 of the arterial blood is 40. So what is the PCO2 of venous blood going to be? That's very good. The PCO2 of venous blood is going to be 45 millimeters of mercury, right? So this is venous. Well, can't even do it anymore. Where do all the veins of the body dump their venous blood? I would be so disappointed if you ever forgot that. Right side. inside your left one. Here it comes. Look. Wait, got to get in that right atrium. And the right ventricle, what the hell? Live a little Timmy. What's the PCO2 of venous blood?
45.
So when the right ventricle sends that blood, pulmonary trunk, left and right pulmonary artery, pulmonary arterioles, yeah, it's going to get down to the level of the alveoli, yes, and the pulmonary capillary. Ain't that right? We'll just get rid of this guy just for a second. Well, I can't get rid of him. Hang on. Get rid of, yeah. What's the PCO2 of venous blood? What? 45. Where do you want the CO2 to go? Into the alveoli. So is the PCO2 in the alveoli going to be higher or lower than the PCO2 in the pulmonary capillary?
Lower.
It's going to be lower. And the PCO2 in the alveoli is 40. So where do things go? High to low. Okay, now watch. Watch. Come on now. And, yeah. When you get into clinical, when you get into the respiratory part, they're going to ask you to understand the oxyhemoglobin dissociation curve and what causes the curve to shift to the right or left. I'm going to explain that to you. Okay? I also explained it to you on that little video I made. Did you watch it? Dee watched it. Yeah, that's good. Here, have a card. Ready? Where do you want the oxygen to bind to a red blood cell? Where do you want it to bind to the iron on hemoglobin? In the lungs. All right? We learned just 10 minutes ago that the PO2 in the alveoli is 100. And the PO2 of venous blood is 40. Ain't that right? And what does increased PO2 do to oxygen's ability to bind to the iron on hemoglobin? It increases it. That's beautiful. Now, what's going to happen to your PCO2 of the blood in the lungs when you get to the pulmonary capillary and the alveoli? The PCO2 should what? Decrease. So a drop in PCO2, where the PCO2 of that newly oxygenated blood is now what? Now what? 40, right? Tell me you see this, right? Because the PCO2 of the venous blood was 45, it went into the lungs, you exhaled it, so this PCO2 of this newly oxygenated blood is now 40. So watch, a drop in PCO2, which you see at the alveoli and the pulmonary capillary, makes oxygen bind to the iron on hemoglobin. Who sees this? Yes or no? That's okay. You'll just get that one wrong. I know, who says that right now?
So, does this have to do with, and I'm just following where this is going, just thinking about it. Does this have to do with acid-base balance?
Yes.
Hemoglobin
Yep.
Therefore, okay.
Yep, and I'm going to let that alone. Just, okay?
Okay.
Now watch. You got a red blood cell. It's yellow. You got hemoglobin. The hemoglobin's really getting ratty. What's embedded in the hemoglobin? What's bound to the iron? What percentage of the irons have an oxygen bound to it in the left ventricle? 96 to 98%. What's the PO2 of that blood in that left ventricle? It's 100. What's the PCO2 of that blood in the left ventricle?
40.
That's very good. So when that blood gets pumped down to the cells of the body, where are you going? Yep. You got me? Hang on. What's going to happen to the PO2, the PCO2, and the oxygen saturation of that red blood cell at the level of the systemic capillary and the cell? So you had a red blood cell, you had hemoglobin, you had iron. What was the saturation of the red blood cell in the arterial end of the capillary? 98 to 90, 96 to 90. Yeah, see, I'm listening to you. Right? What's the PO2 of arterial blood? What's the PCO2 of arterial blood? All right. What's the PO2 inside a cell? What's the PCO2? 45. So watch. As the PO2 begins to drop, because it's going into the cell, what's going to happen to oxygen's ability to hang on to that iron? It is going to go down. So that oxygen can't bind to the iron anymore, and it's going to move into the cell high to low. And as the PCO2 moves into the blood, high levels of PCO2 cause oxygen to fall off the iron on hemoglobin and go into the cell. Say yes. And it makes perfect sense. Where do you want the oxygen to bind? At the alveoli and the pulmonary capillary. Where do you want the oxygen to let go? At the systemic capillary in the cell. And at the systemic capillary in the cell, what are your conditions? Number one, you have low PO2. Low PO2 causes oxygen to dissociate from the iron on hemoglobin. Number two, high PCO2. Say yes. High PCO2, low PO2 cause oxygen to fall off the iron on hemoglobin and go into the cell. What happens when you get to the lungs? What happens in the lungs? The PCO2 goes down and the PO2 goes up. So what are the conditions at the lung? You have numero uno, that's one in Spanish. One, you have high PO2 and you have low PCO2. And those two conditions make oxygen bind to the iron on hemoglobin. Say yes. How many people followed that? Let me just do this and then you can take a break. Okay? Watch. If I'm running, where's the hottest part of my body? I think it's my butt. Come on, that was a little bit funny. What's hemoglobin? It's a protein, and you learned, I'll never forget it, that proteins are temperature and pH sensitive. Ain't that right? Here we go. What? Hang on, I gotta find this. Look at that, man. That looks like majestic, didn't it? Didn't it look like it was kind of like from heaven or something? The capillary from heaven. Okay, watch. He'll have to be metabolically active in his arm. So if dude becomes metabolically active in his arm, that means that dude is going to be using more oxygen, so he will have a low PO2, and he will have a higher than normal PCO2. And when you hack off the third phosphate to make your muscle contract, you're going to produce increased heat. And we learned that will also increase the amount of hydrogen ions, and that will drop the pH. And we oh yeah, I'll never forget this. It was definitely a Monday. Why didn't somebody yell at me with this color? It's atrocious. I'm taking points off. Was that sass there? Okay. You got me? We also know that CO2 is an acid, don't we? Right? So at the most metabolically active parts of your body, the pH will be lower, the temperature will be higher, the PO2 will be lower, and the PCO2 will be higher. All of those conditions cause oxygen to fall off the iron on hemoglobin and go into the cell. And the more of those conditions you have, the more oxygen falls off the iron on hemoglobin. And where do you get those conditions? In cells that are metabolically active. We also learned, too, that these byproducts of metabolism dilate arteries. And where do you need the most oxygen? At the most metabolically active parts of the body. So when the left ventricle contracts, the other parts of the body, you're just working your arm here. We don't know why. So these arteries, my neck hurts. These arteries will remain constricted, and these arteries will be dilated. So when the little left ventricle contracts, where's the vast majority of that oxygenated blood going to go? To the most metabolically active parts of your body. Do you see that? You have to see that. It's perfect. It's perfect. Do you understand that if I would have not explained to you metabolism and the byproducts of metabolism and the fact that they're vasodilated, you would have never gotten that. You get it now, don't you? It's perfect. Yeah. But do you see how perfect that is? So, and I told you day number one, I'll never forget this because I say it every semester. It is metabolism that dictates your physiology. I just showed you today. It's perfect. And watch. When you get a fever, you get a fever all over. So the temperature is higher. What does that do to oxygen's ability to bind to hemoglobin in the lungs? That's why their respiratory rate goes up when you got fever. You don't think that's quality info? Cut it out. Cut it. It does. It makes perfect sense. Okay, you're going to pee. You got pressure diuresis. Micturic. I'm going to explain to you now, and I sort of already did the oxyhemoglobin dissociation curve. I kind of did, but now I'm going to actually show it to you and show you how it works. All right? It's not long. I already explained the length part. No, for real, I kind of did that already. Oh. All right. I can't help that. Oh, I get it. That's another way of saying how does oxygen know to bind to the lungs and let go of hemoglobin when it gets down to the cell? That's the oxyhemoglobin dissociation curve. Right? Oh, there it is right here. Huh. Okay, now watch. Here's a graph with numbers. Look at that. Okay, so watch. Wait, this is the y-axis, right? And this is the x, yeah.
I like that.
Okay, so look, you have oxyhemoglobin saturation, and it's measured as a percent of hemoglobin saturation. You got me? So you got 90%, 100%. Say yeah. You got that? And on the x-axis here, you have PO2. Now watch. Watch. The oxyhemoglobin dissociation curve is sigmoidal. If you can use that in a sentence correctly, yeah. Okay, watch. It's not linear. And the reason it's not linear is in the lungs, as the PO2 increases, every time an oxygen binds to an iron on hemoglobin, it makes the next oxygen bind easier. Do you follow that? So when one oxygen binds to the iron on hemoglobin, it makes the other three bind easier. That's why between a PO2 of 80 and a PO2 of 100, there's not much difference in the saturation of a red blood cell. If it was linear, let's see if I can do this. Watch. If it was linear, it would be like that. And what that means is that if you had a small drop in PO2, you would have a significant drop in the saturation of a red blood cell. And because the PO2 is not always between 80 and 100, right? You go up on the mountain. If you went on the mountain, right, where the PO2 is 60, you got me? Then your saturation would be 60%. You'd be gasping for air and dying. But you go on a mountain where, because of the sigmoidal shape, and the PO2 drops about 85%. That's still compatible with life. Do you got me? Now watch. Here's the other thing. If your PO2 is between 70 and 100, and that's where you find the PO2 of the atmosphere almost everywhere in the world that we live normally, that the saturation of hemoglobin is between about 92 and 98%. You're sending enough oxygen. But this is the important thing. When the PO2 drops below 50%, you get a significant drop in the ability of oxygen to bind to the iron on hemoglobin. So the blood becomes much more difficult to saturate when the PO2s are very low. Are you following me? Now, what they're going to ask you to understand in clinical is you're going to have to understand a shift to the right and a shift to the left. And what that means is that for any given PO2, if you look at this blue solid curve, this is the normal values. A shift to the right in the oxyhemoglobin dissociation curve, what that means is that for any PO2 value, there's less oxygen bound to the iron. That means that hemoglobin saturation is lower. That's a right shift in the curve. If there's a left shift in the curve, denoted by this green dashed line, that means that for any given PO2, there's more oxygen bound to the iron on hemoglobin. Now, I'm going to take this one step further. All right? Watch. When you have a right shift in the curve, you have conditions in your entire body, throughout your entire body, that are consistent with conditions normally found at the cell. What are the conditions normally found at the cell in the systemic capillary? A lower pH, a higher temperature, a low PO2, and a high PCO2. Those are the conditions at the cell. And those conditions cause oxygen to fall out the iron, but it will not allow oxygen to bind in the lungs. Do you understand that? So if you have a low pH all over, not just at your cell, if you're in an acidosis, it's going to cause the curve to shift to the right. What that means is that you won't be able to bind the oxygen in the lungs, and when you get down to the cell, it'll have a harder time letting go. Do you follow that? So what they want you to understand is that if you have these conditions that decrease oxygen's binding to hemoglobin, you have to try to change some of the conditions that will allow it to bind. So if it's low PO2, then you have to jack up the amount of oxygen you're delivering to. If they're in an acidosis, you have to jack up the oxygen you're delivering to them. Say yes. Say yes. You're following this. Now, curves to the left are much less common. But those are the conditions that you would see at the lung and the pulmonary capillary. A higher pH, a lower temperature. What that says is that for any given PO2, oxygen will bind more readily in the lungs. But when it gets down to the cell, it's going to have a hard time letting go. Tell me you got that. But if you look, there's very few conditions where people are going to come in because they're breathing like this. I've been breathing like this for 17 years. Right? So it's not like they're going to have a respiratory alkalosis, or they're going to be freezing to death. If they are, then forget about it. But situations that cause a curve to shift to the right are much more common. Drop in pH, elevated temperature. They got goo in their lungs, so they can't oxygenate, and they can't remove carbon dioxide. So the most common disturbance in terms of the oxyhemoglobin dissociation curve is that it's shifted to the right. And what that means is that for any given PO2, the amount of oxygen bound to the iron on hemoglobin is less than normal.
Does that mean anemia?
It can be anemia. Sure.
Oh, because I thought.
Well, no, because with anemia, then you may be binding all your oxygens, but you don't have a lot of red blood cells.
Oh, okay.
That's assuming you have a normal hemoglobin and hematocrit. Yes or no? How many people follow this? So do I, man. I'm swallowing a bunch of mucus. I'm going to hack a big lung cookie right now. Yes or no? That's the oxyhemoglobin dissociation curve. That's a shift to the right and a shift to the left. And all you need to know, watch, all you need to know when you get into clinical is what are the conditions at the lung and what are the conditions at the cell. At the cell, the conditions cause it to shift to the right. At the lung, it causes the curve to shift to the left.
So, right to left.
Yep. Say yes. Yes or no?
Yes, sir.
Okay. All right. I'm now going to explain to you how oxygen and carbon dioxide are transported in the blood. I explained to you oxygen. I did. I'll never forget it. It was a Monday. I'm going to explain to you how carbon dioxide is transported in the blood. Yes. Do you remember the law of electroneutrality? You're looking at me like I just robbed a bank. Watch. Hang on. Oh. Ready? Thai food? Remember, I told you that the number of positively charged particles in the blood has to be equal to the number of negatively charged particles. Do you remember this? And the number of positively charged particles in the cell equal to the yeah? Is a red blood cell a cell? Good. Good. So, in a red blood cell, you have to have equal numbers of negatively and positively charged particles and equal numbers of negatively charged particles and positively charged particles in the plasma. That's called the law of electroneutrality. You got me? Okay, here we go. I'm going to explain to you how carbon dioxide is transported. And of course, I want this whole thing. What's the PCO2 inside a cell? PCO2. 45. What's the PCO2 of arterial blood?
40.
It's very good. So PCO2 is going to move by pressure from the cell into the plasma until the plasma and cell equilibrate. So one of the ways that carbon dioxide is transported in the blood is dissolved in the plasma, and it's measured as a PCO2. Say yes, CO2.
Yes, yes.
Good. Now, what's the protein inside a red blood cell?
Hemoglobin.
Right? And then you have attached to the hemoglobin, you have this. What's this? It opened up for Menudo at Summerfest. Yeah, the amino group, and they're hit sugar, sugar. Oh, honey, honey. You got me? So carbon dioxide binds to the amino group on hemoglobin. People used to think, wrongly I might add, that carbon dioxide and oxygen competed to bind the iron on here. That's not true. It binds to the amino group on hemoglobin. Now, the most important way is this way. And of course, I want this whole thing. Don't hate, capitulate. My sinuses are really jacked up. I should call in. Is it supposed to be nice out tomorrow? No. All right, then I ain't going to call in. Oh, is it really? Oh, I'm calling in sick. Okay, watch. See? Don't hate, educate. CO2, right? CO2 will diffuse into the plasma of a red blood cell. What's the plasma mostly made out of in a red blood cell? That's very, well, we don't want to say that. Well, yeah, I'll give you that. Okay, today I will. What are you doing? Tying an Indian knot? What? CO2 will combine with water. Ow! Ow! And inside a red blood cell, that red blood cell is loaded with an enzyme, Anna. Do you know what that enzyme is? Carbonic, yeah, carbonic anhydrase. And CO2 and water will form what? Please, you better get this. That's right. And carbonic acid will then dissociate into what? Hydrogen ions and bicarbonate ions. Now watch. Anything that produces free-floating hydrogen, free-floating, is an acid. But we learned, I'll never forget it, quiz number 1, some of you actually even wrote it there, Kristen, that hemoglobin is a buffer. And the hydrogen ions will kind of nestle up and bind with the hemoglobin to buffer them. Now you got this bicarbonate. Bicarbonate is readily diffusible from the plasma of the red blood cell into the blood plasma. Are you with me? Who's following this? But now you have put out a negatively charged particle. So to maintain the law of electroneutrality, a negatively charged particle moves in. And that negatively charged particle is chloride. That's the chloride shift. See, you read that in your book and you had no idea what was going on. And then Timmy came in and he explained it to you. Yeah, here. Who wants to swig off my Diet Coke? You can't be. You can't be. I explained that perfectly.
No, I think I'm a little back farther.
Okay. CO2 is an acid.
Yeah, I got that. I got that it goes CO2 and H2O makes carbonic acid that'll break down into bicarbonate and hydrogen ions.
Yes, then the hydrogen ion is buffered by the hemoglobin, so it binds to it. You got me? So it's not free-floating, because remember, the only thing that affects the pH is free-floating hydrogen ions. Ain't that right? So now you got that negatively charged bicarbonate, and that will diffuse from the plasma of the red blood cell into the plasma of the blood. And because it's negatively charged, to maintain that law of electroneutrality, chloride has to come in. And that process, this happens at the cell. And that process is reversed in the lungs. Now, this is an example of an enzyme that can go both ways. Because the CO2 is high here, it's going to force the equation this way. So carbonic anhydrase is going to take CO2 and water and form carbonic acid. When you get to the lungs, carbonic anhydrase is going to take the carbonic acid and break it down to CO2 and water. What?
Chloride is just in your blood because...
Chloride helps maintain acid-base balance. It does. I kind of lied to you, but it was for your own good. When you throw up, you're actually throwing up chloride ions too, and that actually makes your blood become more basic because the bicarbonate is shifting due to the decrease in chloride. So chloride and bicarbonate kind of, they trade places. And that's to maintain the law of electroneutrality. Say yeah. How many people are with me? Okay. I want that whole thing. What? It ain't bad. Okay. Don't worry. You're going to study it real good. Okay. One more thing and then you can ambulate home, okay? Man, I'm really not feeling good. You know, you guys are very caring about me. You know, you worry about me, don't you? Right? You probably lose sleep. Yeah, a little. Yeah. Yeah. Oh God, yeah. Yeah. Are you kidding me? Look, if I couldn't take it, I wouldn't dish it out. Do you understand? Okay, here we go. Have you ever seen someone who's died from carbon monoxide poisoning? They have never looked healthier in their life. They look just, they are. They look like they're pregnant. Don't they look nice? Don't they?
Someone said that's the most ideal way to die.
Well, it depends if you do it right. You know what I mean? You don't want to, what people do is they stick a hose in their tailpipe and then they put the hose into their window. No. You just turn on your car in the garage. Because rapid accumulation of carbon monoxide stimulates vomiting. So you'll vomit to death. You'll vomit before you die. You don't want that. You just want to kind of fall asleep. Now, watch. Here's a red blood cell. That's okay. And what's the protein inside a red blood cell? And what's in a hemoglobin that oxygen binds to? We know there's 4, and there's a lot of hemoglobin, but we're only going to put 1. Now, carbon monoxide is odorless and colorless, so you don't know that it's affecting you. But carbon monoxide, not cardiac output, CO and oxygen compete for binding of iron. You got me? Now, what does oxygen do when it gets down to the cells? It dissociates, right? Carbon monoxide, once it's bound to the iron, does not dissociate. So even though you're breathing in small amounts of carbon monoxide, that carbon monoxide is bound really, really tight to that iron. So every time that oxygen circulates and you're still exposed to the carbon monoxide, it is going to pick up more carbon monoxide, and that will allow you to deliver less oxygen to the cells of the body.
But is this why you told us if they have a pulse ox on, we shouldn't
Right.
They'll be showing 96 to 98.
So if someone is developing carbon monoxide poisoning, carbon monoxide, when it binds to oxygen or binds to iron, turns the blood red. That's why they look really good. Their lips are nice and rosy, and their cheeks are rosy. But they're dead because they can't deliver the oxygen, so they asphyxiate themselves. Tell me you got that. Yes, and remember, oxygen lets go when it gets down to the cell. Carbon monoxide doesn't. So every time that blood circulates and you're still exposed to carbon monoxide, it's going to bind to more iron. So it depends on how fast you've been exposed to it.
How much carbon monoxide can one hemoglobin?
4. Until you completely asphyxiate yourself. And then it's all right. Yeah.
It's still there, so that won't pick up anything.
There you go.
Right. So it competes with oxygen. Normally oxygen will fall off at the cell, but carbon monoxide stays.
It doesn't.
And the carbon monoxide is spastic, usually.
Yes, it binds much more readily. Yep.
Oxyhemoglobin dissociation curve, then once you hit that particular, hit the 50, then it's just going to
yes, yeah. And as soon as it starts plummeting, then more of the carbon monoxide can bind. So small, parts per billion of carbon monoxide will kill people. So burning fossil fuels, right? Having a poor, functioning gas heater, right? Or a poor functioning furnace that doesn't vent well. That's why. And a couple of years ago in Milwaukee, there was a couple of kids. They were probably, 54, 55 years old. Their parents wouldn't let them have sex in the house, so they went into the garage and had sex in the car, and it was cold, so they turned it on, and they found them dead. And because you can't smell it, you don't know that it's happening. So usually carbon monoxide is slightly lighter than air. So it will start affecting people higher up. That's why in the mines they would have birds hanging up there. So if the bird fell over dead, they knew it. Maybe get our fatty acids out of there. Yeah. Yeah. So what they do is that it's a partial pressure. So look, I had this one dude a couple years ago. Student. He normally sat there, and a girl came in and sat there. So this is what he did. And I'm like, do we have a problem? And he's like, she's sitting in my chair. And I'm like, is someone eating your porridge? I mean, come on, dude. Anyways, watch. So if you ask someone nicely to move, and they do it, then you're fine. But if they're not going to move, then you have to push them. So what you do is by bumping up the PO2, so when they come out, you find them in the house or the car, whatever, you put 100% oxygen on them, and that increases the PO2. Sometimes that's enough to push the carbon monoxide off, and you're straight. If that ain't enough, then you have to go to what's called a hyperbaric chamber, where they can pump the PO2s up, not to like 100, they can pump it up to 600, 700. And that's enough where you better get out of my way, right? Where you ram that carbon monoxide off the iron. Hyperbaric.
So usually that's 100% oxygen.
It depends on how much they've been exposed to. So what I'm looking for is that you bump up the PO2, the pressure, to force the carbon monoxide off the iron. If that doesn't work, then you put them in a hyperbaric chamber, and that will really force the carbon monoxide off them. But that's the thing. It's like you don't know that until they wake up dead. So
if they come in walking and they just think they're exposed, the smartest thing would do is put them on oxygen.
Give them oxygen.
Because you're not going to rely on the pulse ox. So if they were traveling in their RV, and, like the truck, the kids were out there sleeping and they died. Because all of them were not on the other side. Oh, they were just burned. I had a friend of mine who just like 3 months ago had to do the hyperbaric.
It's awful. That's why everyone should have a little carbon monoxide detector, and I check mine like 20, 30 times a day. As a matter of fact, I have to go home right now and check it. But no, it's true. And especially people who, like if their gas and light gets cut off, then they use like space heaters, and those are the people that usually end up dying from that. Yeah. They're not well vented. They're burning fossil fuel, and they're not 100% efficient, so you're releasing carbon monoxide. That's why, like, dryers, right, house dryers, when you vent, they had, like, a little vent so you can blow that kind of cool and warm, moist air into your basin. That has carbon monoxide in it. So if you're running your dryer a lot, you don't want to be doing that. Well, yeah, most of it's vented outside, but some, you've seen it where you got like a little thing where you can open it up in the wintertime to kind of put some moisture in your basement when you're drying your clothes. Don't do that. It can end up killing you. And then how would you go to Gateway? Yeah, you'd have to ambulate home. Okay, we're done. We did good. Okay, so